Well, for those of you who have tuned in to stage 2, we're talking about how to build and scale your Appian platform. This is the architecture masterclass, so hopefully you're in the right place. If you're not and you want to switch, it won't hurt my feelings. I'll try not to notice halfway through if you do that. So, to begin, I wanted to illustrate, sometimes if you've ever been to a massive geographical feature like the Grand Canyon, you stand at the edge, you really get a sense of scale. And that's what we're talking about today is scale. It can be exhilarating and a little scary at the same time. And that's a little bit how we feel sometimes when we have a very successful use of the Appian platform and it is growing and we need to scale. And we start to realize just how massive things are. So what I want to talk about today is a number of things, and Sylvan and I are going to talk about what we've learned in the number of years that we've been running Appian as a platform on our cloud, and as well how we have learned from our customers, different patterns, different design patterns that are built for scale, and go through that. I'm going to talk a lot about the details of the software components. I'm going to talk about the process engines and how to scale those and various other software and hardware scaling considerations. All of these, again, are lessons that we've learned from cloud, and I'm going to be talking about some key indicators that you can look at, but we're also monitoring those. For those of you who are in the cloud, we're looking at these same key indicators that I'm going to talk about today to determine if your use of Appian is ready for that next bump up, either in hardware or software component architecture. But before all that, I wanted to talk about an exciting announcement that we have here at Appian World 2018. For the first time, we are documenting and providing some tooling and scripts for running Appian in Docker. Containerization is very clearly the future of the way to deploy software. We're going to be adopting it in our cloud. We're in the process of doing that now. We have made enough progress that we're also ready for you to start giving us feedback. And so as a preview, we recommend not running this in production yet, but in development environments, test environments, to quickly spin up Appian instances. This is going to greatly reduce your time to deploy. We have a really simplified deployment. You create Docker images using the scripts that we're providing, and we have Docker Compose to orchestrate the various containers. And as you can see here in the illustration, we have 6 containers that were by default, and we have Appian Engines, Appian Data Server, and Appian Search Server are the Appian components, and then we'll create an image of JBoss for you. We'll create an image of MySQL, and optionally you can create an Apache web server image as well. And again, that Docker Compose that we're shipping as part of the documentation will tie all those together. Okay, so moving on to the scaling aspects. I'm using this slide just to illustrate the architecture, the software architecture of Appian. It is deliberately unstylized. I really just want to give you a context for how these pieces fit together. So at the top we have our web interfaces and mobile interfaces, that which users interact with. We have below that the web server, which is serving the request for the users. And of course below that the middle tier, that application server where a lot of business logic is handling a lot of the logic for the application platform. And below that we have the Appian Engines, the Appian Data Server, Appian Search Server. Those things that I just mentioned as being containerized are the rest of the components there. And I want to call your attention to the one that's bold there, the Appian Engines, because that's where we're going to focus our first bit of talk about scaling. So I've exploded that gray box into slightly more stylized and colorful box containing the various software components that we consider the Appian engines. So at the top here we have the service manager that's responsible for directing the traffic between the engines for when a transaction comes in, determining which engine it needs to go to. We use Kafka to handle the transaction log so that transactions are persisted in that transaction log and can be replicated from there, and I'll talk about what that means later. And Zookeeper kind of keeps everything all organized and all together. Directly below that, we have a number of engines listed there. Those are just different software components of our engine architecture. I'm not going to go into detail on those that are on the right side. On the left side here, I am going to draw a little bit more attention. We're going to talk a bit about that because that's one of the areas where we find scaling to be the most useful and the first place that people need to scale is in the process engine. So at the top we have the process design engine. That's responsible for handling process models and starting processes. And then we have pairs of process execution engines and process analytics engines. And by default, there are 3 of those pairs of sharded process execution and process analytics. I'm going to go into some detail about what that means in a second. So the types of scaling that we think about are read scaling and throughput scaling. And there's different ways of detecting whether you need one or the other, and I'll tell you about that. And there's different strategies for how to actually achieve scale on these 2 dimensions, reading and throughput or writing. Before I get into that, I kind of have to explain how processes are organized across the various shards. So here I've illustrated, I've blown out that stack of 3 into 3 pairs here of process execution and process analytics. And when a process starts on one of those process execution engines, we generally round robin across them to try to balance the load between process execution. When one starts on there, its data is replicated to a corresponding process analytics engine. So they're always come in pairs. The reads are typically coming from that process analytics engine. We're doing reporting off of that, and that handles most of the read load. Most of the write load and that transactional throughput of process flow is actually occurring in the process execution engine, and then incrementally updating the analytics engine with data so that it can continue to be read. So when that second process starts, it might start on process execution 2, and its data replicated to process analytics 3 or 2, and same for the third. Okay, so now that you know that, now we're going to get into some of the details. So here is the first of the key indicators to look for to determine if you need read scaling. That first indicator is in a log called the engine call summary, and there is a set of columns called other time. But you essentially think of other time, perhaps poorly named, as the time that as a user, that your request is waiting on other requests. So we're measuring that, and as that is increasing or has a sustained high value, then you'll probably benefit from read scaling. You're probably at that point where you need to start thinking about read scaling. Read scaling is most effective when you have a high ratio of read and write counts. So read to write count is high. Typically, and again, we monitor all of this for all of our cloud instances, we're seeing typically applications are built in a way that 80 to 90% of those transactions are actually reads. So there's a lot of reading going on, and the writing is happening too, but that's kind of a typical range. So as long as that's high, like in that range, then you're going to be good for read scaling. Another indicator to look at is if you have significant delays during checkpointing. This is when you have a standalone instance and the data checkpoints. The data is actually checkpointed based on some frequency that's determined based on how long it might take to replay and transactions. The details aren't important here. Those can be seen in the documentation. But that's an indication that you might benefit from read scaling. And I want to point out this is for on-premises only. In cloud, even with single instances that aren't read scaled, we have done some tweaks behind the scenes at the OS kernel level to figure out how to do checkpointing that doesn't require any kind of delay. So what does read scaling look like? It's actually copies of that data. So I've illustrated here the same thing that I showed you earlier, the 3 pairs of process execution and analytics, and they're copied to additional servers. And this is actually the exact same structure as our high availability offering. Our high availability configuration is this. We have 3 servers. If you're on Appian Cloud, we actually run these 3 servers in different availability zones. And so you get data redundancy, but based on the topic here, scaling, the emphasis here is that we are also doing reads across all of these. So a read can go to any of these, and therefore it will allow for more simultaneous reads. Okay, so thinking back to the throughput type of scaling, one of the key indicators for that is a sustained low CPU idle time percentage. And this is basically how much time does my CPU have to do work? And if it doesn't have very much time to do other work, it means you're really pegging it. And that can be found in one of the process execution performance monitoring log. Now the key here is you can take advantage of more CPUs if you have them. So you would only add more execution analytics shards if you had the CPUs to support them. So what does throughput scaling look like? So we have our 1 through 3 that come by default. You can just add another. And you can keep adding another and another and another pair up until you get 32. And that's new in Appian 18.2, announced here at Appian World. We used to have a limit of 16. We'll now allow you to go up to 32. So we've doubled the number of execution engine and execution analytics pairs. And that really allows for much greater throughput. So much so that it's illustrated here. So this is a graph of the smart services executed per hour and some testing that we've done. So on the y-axis, we have how many smart services were able to be executed. And on the x-axis there at the bottom, we have the execution engine count. So how many pairs of execution analytics were tested. And on the far left here, we have the default, right? So at the bottom is somewhere around, I don't know, what is that, 500,000 or so per hour? But then at the top end, up at 32, we can do over 3 million per hour. So that's kind of the profile of how we can scale. And the previous limit was at 16, so you can kind of see that was just above 2 million per hour. So we've gotten up to 3 million per hour in this particular test. Mileage, it will vary because our test model is definitely different than your test model, but really what we're trying to isolate here is actually the smart service execution count. So that's a great thing if you're at that border already. You can now in 18.2 go up. And of course, you can do read scaling and throughput scaling together. So through the high availability offering, you can have 3 servers through that configuration, and you can also go up to 32 pairs on each of those servers. So that's a lot of capacity. So again, use read scaling to get more queries, more query throughput. And the bonus here with high availability is you have data redundancy. And then, of course, use throughput scaling for more processing, and just keep adding up until you have exhausted all the CPUs you can take advantage of. Okay, so I've talked about process scaling for a bit. I want to talk a little bit about other scaling strategies, other architecture scaling strategies. The 2 other things that you can do in terms of scaling are add more hardware, so either more CPUs and RAM, or add more application servers. And I'll tell you the reasons why you might want to do one or the other. So one of the key indicators for adding more hardware is load average. If that load average is greater than your CPU core count, and these are, again, in logs that you can inspect for if you're on premises, and we're already monitoring them if you're on cloud. If it's greater than that CPU core count for an extended period of time, then you are a candidate for needing more CPUs. You're exhausting the capacity that you currently have, and you need more. And similarly with memory, we have a measurement of total memory, and if that used system memory goes above that total memory, that means you're using more memory than your system actually has, and the OS is trying to handle that in inefficient ways behind the scenes, and it will benefit you to have more RAM. I mentioned earlier about how many CPUs you can take advantage of, and I just wanted to illustrate that here. You can add CPUs, and you might need to. By default, each of these components that I've labeled with a number can take advantage of 1 CPU at a time, at most 1 CPU. If you have fewer than 18 CPUs, you may be benefiting from adding more CPUs so that you have more capacity for these things to take advantage of them. Okay, now I want to talk a little bit about the application server scaling. And I wanted to illustrate this with a graphic about the way our distributed installation. So if you think back to that original architecture diagram that I showed, this is a simpler even than that. And so we have an application server, we have our Appian engines, and an RDBMS on separate machines, let's say. Or they could be on the same machine. The application server, I was saying earlier, does a lot of work that's brokered between the engines and the RDBMS, and of course it's doing a lot of processing as well. All the expression evaluation is taking place in the application server. So when you look at that and you look at the a consistently high or increasing Java work queue size, then it means that you may benefit from having more application servers to do that work. That would be true only if the total completion time is fairly flat. So that's measuring how long it took to do the work. If that total completion time is actually going up, then you probably have a bottleneck somewhere else. You're not going to necessarily benefit from getting more out of an application server. You are probably looking at an RDBMS or a web service down the line that's to blame for your latency or performance issues. And so that's where you might want to look for that. And so what does it look like? Well, you just keep adding application servers, and you can add a few more. We do this rarely in cloud, so typically I started with the ones that are the most common, process execution and of course read scalability. But there are occasions where we've done this, and on premises, of course, customers have done this as well. Typically one application server is sufficient, but depending on the way that your particular system is using Appian, you may benefit from more than one, and so you can just keep scaling them out. Okay, with that, I'd like to turn it over to Sylvan to talk a little bit about some design patterns, to think about the software that you build, the applications you design in Appian, and how you might scale those. Thank you.
Thank you, Brett.
Yep.
Can everybody hear me okay? Yes, thank you. Sorry. So my name is Sylvain. I work in PS, Professional Services Department, and I've been working with customers for 11 years now. So I've seen a lot of different design for application, a lot of different use cases. And as Brett mentioned, what we want to go over today is some of the design patterns that will allow you to scale your applications past 1,000, 2,000, 10,000 users, millions of processes, because Appian is a very high productivity tool in a sense that it's low code. It allows you to develop applications very fast, but it's contradict with the more high control type application where you can very granularly define what's going to happen in the backend, how the application is built. So as a low code tool, Appian allows you to build application very easily and very fast, but when you want a very large scale due to the volume of the processes, the volume of the users, we have design patterns that will allow you to do that. The first one I want to talk about is the classic design pattern that we use on most of the applications that we develop these days. We do this every day at Appian for most of our customers. It is the data-centric or record-centric design. So this should be your to-go design for all of the applications that you develop. This is not what we used to do in the past, before we had record, before we had sail and rich UI. This relies on the user navigating to the UI and identifying what the next task needs to be done. You have your data all over the place here, in diagrams, in grid, in list, and interlaced into this, we can put a lot of different ways for the user to take an action. So as a user, if you log to the system and you navigate to that record, you may say, oh, well, based on the price of the stock today, I need to take this action, and I will click on one of these little blue buttons in the middle here. Oh, I need to start a brand new onboarding process, so I will click on one of these card layout I have at the bottom right corner, one of the new Appian UI widget that we have. We also have a way to put actions, related actions, so there's a lot of ways for us to add actions in the middle of your data for your experienced user to take actions on the data. This is not to say that you cannot have a process with a task assigned to the user, and the user could not navigate to the task list. But this is way much more scalable than what we used to do in the past. And the reason is that when a user navigates to this dashboard or to this record, there is actually no process behind the scene. So all of the data that is rendered here is being pulled from external systems such as databases, ERP, web services, and aggregated here on the screen live through the application server. So the engines are not involved. As Brett was saying before, the execution engine actually doesn't have a process running at this point for the screen to be rendered. The processes are started on demand when the user clicks on one of these buttons to take an action. Behind the scene, the process is started, and through activity chaining, you can go through some of these screens, and then the user eventually come back to that screen here, to the record dashboard, to take maybe the next action or to navigate to a different record. So this relies obviously on processing starting on demand. This is We have this new feature in Appian called the Start Process Link that allows you to start a process by clicking on the button and activating directly to the first UI. So this is a key concept that we use here. This is also enabled by very rich UIs, like you've heard throughout the conference, the ability to really aggregate and condense a lot of data on the screen so the user can take the action based on the context. You don't have to have the user navigate 3 levels down to sub-processes or different dashboards. You can pile up a lot of data here so the user can know what's going on, have the right context, and take the right action. As I mentioned already, the actions are right there through one click, and because all the data is being aggregated in live, it's not replicated in Appian. Right? We don't need to own your data. We just need to have access to it, be able to represent it, and we just take action on it through processes. So this should be your first go-to design pattern. This is very important. Like most of the applications should be built that way. Not to say that you could not have processes, of course you can, but this is really how you should think about designing an application if you start fresh. The rest of the design pattern that we are going to look at today are an evolution or a next step based on this. And it's really important. I really want to stress that this is really should be your default. The other pattern that we are going to see should only be used if there is a need for it. If you, let's say, you start millions of processes per month, and you know that in the engines it's going to be such a load that you cannot have all of them running at the same time, then maybe use one of this next pattern we are going to talk about. But it's a sliding scale. You should not go directly for the last pattern that we are going to discuss because you probably not need it. And there is a cost to it. Right? It's more complex, it's harder to maintain, you need more experienced designers to do it. So as we go through the patterns, I will keep reminding you of this, but really this one is the main one that, if you remember one thing, remember this one. Okay, so the second pattern is about standalone cell UI. And just give me 1 second. So to illustrate this, I just want to take a very simple example of this process here. Think about it as a task being assigned to a technician as one of your process. The user logs into Appian, navigate to a record, for example, click on one of the action, and then his activity chain to the first task with a cell form in it. And before that, we grab some data through a third-party system, probably web services. The data is shown on the screen to the user. The user enrich the data, fill up the form, and once the user clicks the submit button, we persist the data back to the database. We write some task metadata, and then we complete. So this is great. This is very classic. We do this all the time. The concept about standalone cell UI is because most of these things now are available in cell, right? Through the cell interface, directly on the screen in your cell code. So after you drag and drop your component and you design your UI, if you go to the expression view of this, you can add web services, you can add query database node through query entities. So you could grab the data directly in the cell UI. You don't have to have a node before this in your process. And in the same way, once the user clicks on the submit button, you could persist the data back in the database through the ABank write to data store function that we have, or you could also write it through a web service if you want to, directly again from the UI. So all of these nodes that are on the left and on the right of this task could be removed because you could aggregate everything into that one task. So then taking it a step further, then why do you even need a task to begin with, right? The process here is redundant. If everything is available for you to be done in that one node, in cell directly, then you don't need a process. You could have this directly in the UI. So if you think about the screenshot we looked at previously, when a user clicked on one of these buttons, that could flip the cell UI to a form. The user can fill up the form. When you click the next button, we could flip this to a new cell UI. There'll be persist data in the middle, query more data for the next screen. And when the user clicks the final submit button, we write the data directly from the UI and show you back the first screen that you were seeing. Again, no processes, all done through the cell. It's very powerful. The key concept here is that, again, the data is persisted and queried from the UI directly. Cell wizards are replacing activity chain processes. And in the case where there is a lot of complex processing or there is a lot of different systems you need to persist the data to that cannot be done in cell, you can obviously start a process to take care of this. Once the user clicks on the final button, start a process asynchronously that takes care of it and then go back to the main screen for the user to keep working. So this is very powerful. Again, remembering what I said earlier, that this use case doesn't apply all the time, this is also more complex. You need someone that really understands the sales code to do this. Like drag and drop on the UI will only get you to having a nice looking UI. If you want to be able to query data and write data directly from Sail, you need someone that really understands how this works. So a little bit more advanced designer. The other thing is that you don't have a process anymore. So it's very hard for the next developer that comes in to understand directly what's going on. Like one of the great things about process is that it looks great. When you look at it, you know what's going on. You know that I'm querying data, I'm assigning a task, I'm writing data. But if you replace this by a set expression, then it's a little harder. Or you don't have a design flow in Sail. You just have a bunch of rules that are nested within each other. So it's a little bit more complex to understand. However, again, if you were to have 100,000 of these tasks assigned to user every day, you may not want to start that many processes. It's just a lot of processes, a lot of load in the engine. So replacing it with Sail means that the engines are going to be left alone, be able to do whatever other processing that needs to happen, and all of this is going to be done in the application server as soon as the user clicks on the button. So very powerful. The next use case is, again, an evolution on top of this to what I call the database-backed task list. We have had several discussions with other architects in professional services about this, and there is use cases for this. It is, but because it's so different than how we used to do things, I really recommend that you weigh the pros and cons of this design pattern before you adopt it. And we're going to go through this in detail later, but I just want to caveat this one by saying that it is somewhat different than what we used to do. So to illustrate this, I want to go through this use case, which is a very simple use case, similar to the one we just saw earlier. You have a process with two users. You have a technician and a quality engineer. And as this process, when you start it, you get some data, you assign a task to the technician do his work, enrich the data, submits it. That goes to the quality engineer who do the final checks, make sure everything is okay, and eventually submit the task, which passes data to the database and maybe send a notification. So it's a very simple, typical Appian process. There is nothing fancy about it. The problem with this is that if you have 1 million of these processes, there's going to be a lot of stuff in your engines, right? Even if the users are not ready to work because it's at night, or they're on vacation, or for whatever other reason, you still have 1 million processes in the system running, waiting for someone to take a task. And they will all be stuck at the same place, either on the technician task or on the quality engineer task. There is nothing happening. The processes just live in memory in the engines and just consume resources. But the system is actually not doing anything. So instead of this, one possible alternate pattern will be to move away from this process task to a database task, which means that instead of having a process and doing a process report to see the list of tasks, potentially you could get this data from the database directly. So what it would look like is something like this. So the first step of the process here is that you start the process, you grab data, and you assign the task to the technician. Instead of doing this, you could start a process, write data in the database, to say, hey, there is a new task for the technician. Here's the task metadata. This is the name. This is the date he was assigned. This is who should be completing it, and end the process. When you do this, there is no more process anymore. There's just one more row in the database. When the technician logs into the system, give him a nice dashboard with a task list that is populated from the database directly. So as opposed to querying the data from the analytics engines and say, like, here is all my processes running and it's all my process tasks, query the data from the database with a normal EBEN query entity and say, like, here's all the tasks assigned to the technician, displaying to a nice little grid in Appian, and using the start process link that we saw. When you click on it, start this process here. This process will activity chain directly to the technician task, grabbing the data that you need on the way. And once the technician is done, the data is written back to the database, the KPI metrics are also updated, and the important thing is that last node here will write the metadata for the next task, which is assigned to the engineer. So again, Once that user is done with his task, the process is completed, the process is gone. The next task is in a database. So there is not yet another process running, waiting for the quality engineer to pick it up. It could be weeks, months before this task is picked up. You don't need a process for this. And then similarly, the last piece of it is the quality engineer task. Same thing, logs into the system, see a grid, data is coming from the database, click on it, that starts this process, and once it's done, we just persist it and complete it. You could combine this with the previous pattern too. So you could have no process, no UI, no nothing. I mean, at this point, it gets very complicated. But again, I want to stress the fact that the design patterns are advanced. You need someone that really knows what they are doing to design this, because there's these 3 processes here that represent the same very simple process we saw at the beginning of this pattern are harder to read. Like a normal designer that doesn't have a context of the application, doesn't really know what's going on, will have a lot of trouble going through this. So they are very powerful, but they also come to a cost. The key concept here, we've seen them, there is no running processes. The tasks are not process tasks, they are database tasks, so just the metadata. And the task lists are not process report, they are just reports coming from the database. And then the processes are all on demand. Like if nobody is currently working in the system, you have 0 processes running, meaning the engines are empty, like the system is happy. So very powerful. One more caveat on this one that I haven't put on the screen is that if you use a normal process task, you get all of the benefit of Appian in terms of task escalation, task reassignment, exception flow. So all of these features that comes with like a normal task do not exist here. So you are trading this high productivity, high flexibility system for more control in terms of management of resources and memory and scalability. So again, think about this trade-off, right? This doesn't apply for every use cases. I would not recommend this if you are just creating an application tomorrow. You have to really think about how many tasks am I going to have, how long the tasks are going to be in a system, how many processes will I get in 1 month, 6 months, do I actually need this? Because if you do, there is a cost to it, right? If you need task reassignment, then you have to design it in the process. So there is more you need to think about than just, I don't want you to live here and refactor your application. This is something that you need to think through.
Anytime Appian gets into a new market or doing it, we have our goal of trying to create something that's very powerful and make it.
The next 2 design patterns are slightly different than the 3 that we've first seen, in a sense that they don't apply to, they are not user-facing, they are more back-end facing. So the use case is not, there's a task for a user, the user needs to complete it. The use case is more, I need to process a very large amount of data very fast because I'm doing ETL from one system to the other, or I'm processing a batch of requests coming from external system to dump in my database or to start processes. So it's not user-facing, it's more a lot of data processing. A typical use case is an ETL. And to talk through this, I have a very simple process here where, as part of a nightly batch, you are reading from a data source, let's say a database, a lot of data. And then for each of these lines in the database, each of these rows, you are going to start a process to maybe enrich the data, call another database to query more, call web services to add more records, and eventually write it somewhere else. So it's very classic to do these kind of things, to process data in batch on a nightly basis. As an example here, I say maybe you do it 10,000 times a night. Maybe you do it 100,000 times a night, right? It doesn't matter, like a very high number. This, based on what this process does here, you could be running into problems, right? Imagine that you run this in the middle of the night and it takes so long to complete that once the user comes to the system in the morning, it's not done. Most of the resources are going to be used by this process, and then the users are going to have a terrible experience. The UI is going to be slow, the processes are not complete fast enough, so you're going to run into a problem. The other thing that you want to consider when you do these kind of things is that if Appian is integrating with another database or with another web services, and you start with 10,000 of these processes, you may get into timeout from this external system, right? They may not be able to handle 10,000 calls at once. And they may time out, the processes may error out because you cannot continue, and then you will have a lot of manual process, potentially to restore the flow and keep going and finish your batches. So it's important that when you have this kind of use cases, you don't throw everything at it and then hope it completes. You have to go through some performance testing, some evaluation to make sure that it works properly. And if it does not, then you use what I call process execution throttling, which just means that instead of throwing everything at it and hope that it's good, you're going to break it up in small chunks, in batches. And so instead, from this two-node process that we saw earlier, you can have something like this, which is a loop made in the process that will process this data in batches. You will get the first batch of data, let's say here 100. You'll start 100 sub-processes to tackle it. You wait, and then you loop again and again until the batch is done. So two things that are very important on this diagram. The first one is the process, the blue node here on the far right corner. I don't know if you noticed on the previous slide, I was using a sub-process node. Here I'm using a start process node, so it's very different. The start process node is a faster, more efficient way to start a process. And more importantly, it will load balance this new process across any of the execution engines that are still in a system. So as opposed to a sub-process that will start the other process on the same execution engine, this one will load balance. So you get way better scalability, way faster throughput if you use that node. And the other important node here is the wait timer that you see at the top. That will more or less stop this process, or put it on pause, I should say, leave the system, handle these 100 sub-processes, do the integration, do the wrap-up, and then move forward. The value that you have to put in the timer really depends based on what these sub-processes do, how fast they can be tackled, what are your SLAs to go through the entire batch. So it's you kind of trial and errors to see what's going on and what the right value should be. But the important thing is that you are throttling the execution so that you don't flood Appian, your external system, and consume all of the resources so that the end user may not have access to your environment. I think I mentioned everything that we have here. The data is processed in batches, all load balanced, and using timer to break it up a bit. All right, and so the last design pattern that I want to talk about is, I touched base on this a little bit, the difference between high control system, where you really want to control what's going on in terms of resource allocation, memory consumptions, versus a high productivity system, which is a low-code platform like Appian, where everything can be built very fast from the UI, drag and drop, low code. So this pattern addresses what happens when the flexibility that you get from Appian is just not enough to tackle what you need to do. Going back to the previous example, if you had, let's say, 1 million of these batch jobs to do per night, starting 1 million processes may not complete in your SLA window, let's say 2 hours. In that case, you're stuck, right? You develop these very complex processes with all of this integration, and you just don't have enough time to run through it. It doesn't matter how many engines and CPU you throw at it, at some point, everything has a limit. So that's why you will switch from this high productivity system to a plugin, right? Everything that you've done through your process model, then maybe consider taking that logic and moving it to a Java plugin. As the name says, it's done in Java, so you have all of the flexibility of the Java language. You can do multiple threads, you can do integration, you can do your data processing and transformation all into one node. And that node will run exclusively in Java, so in the application server. Well, except maybe if you do calls to the engines to get data, but otherwise it will be done in Java. So you get the scalability of your application server, the power and speed of Java, and you don't have to bother the engines. They can keep doing whatever they're doing, processing the user request, whatever that is. So from my experience, when we did this move to a Java plugin, we saw the execution be so much faster. Everything completed in seconds as opposed to like a minute or more. So it's very powerful. But again, you need someone that knows Java for this. Right? Your designer may not have experience in Java to do it, or if they know Java, they may not know Java enough to be able to use multiple threads, integration, database connections. So it's kind of a different type of development at this point. It's not drag and drop Appian, it's more high control Java. A plugin is like any other Java application. It runs in the application server in an isolated class loader, so you won't mess up the rest of your instances. And it's a very powerful design pattern if you need to complete batch or large amount of data or processing in a very short term. Again, that shouldn't be your first choice, obviously. It requires different set of skills, but it is kind of the ultimate way to scale something in Appian where the processes can't get you to that point. Last slide that I have today is just I want you to read this quickly. I'm not gonna read it for you. It's just a list of different features that we have in Appian or different tools that are available to you when you think about scaling either your hardware or your software. Or you can see here some of the design tools like the start process functions, the Appian health check, performance testing. So all of the kind of things that you need to think about, not when you develop a normal application or a standard application, I should say, but when you start having very high volumes, a lot of users, a lot of processes, where you have some due diligence to do in order to make sure that it's going to work and scale properly. As a conclusion, I just want to leave you with some of these resources for you to learn more about scaling Appian and to keep going on your journey. Obviously, stay current with Appian. Always get the latest version and latest hotfix. We make the platform better and faster with every release. It's very important. If possible, move to Appian Cloud. We would love to host your system. As you saw through Appian World, we have an amazing staff. We have very high SLAs and uptime. And we will do all the management of the hardware for you guys, all the monitoring. We have different resources on the playbook and the documentation that you should review in terms of scaling the hardware and scaling your application, all of these design patterns and much more. And finally, to get a quick view of how the system is performing, how much memory you are using, what are the processes that are using the most memory versus the other one, what are the rules and functions that can be optimized. I recommend that you check out the Appian Health Check. That gives you a very good overview of your system and what's going on. Thank you.
Thank you very much.